Continuing on the theme of carbon capture and storage, Reza Rahemi, CO2-induced seismicity and the policy path forward with quantum materials. Reza, the floor is yours.
Oh, hello, everyone. I hope you're having a good time. So my topic is CO2-induced seismicity and the policy path forward with quantum materials. Before diving into the issue, let me tell you a bit about myself. I'm a solid-state physicist who is interested in modeling and data assimilation. I chose to bring awareness to the problem of CO2-induced seismicity because climate tech is desperately in need of new and adaptive technologies which arise from engagement of different disciplines. Here is my equation on quantum materials published in the most cited journal in material science, and I will explain how advanced materials may help us survive in this warming climate. When it comes to helping the environment, I believe we should use everything at our disposal to tackle the problem. And it involves a multidisciplinary approach. Quantum materials are materials which exhibit extraordinary properties which cannot be explained by classical physics. In other words, you would need quantum field theories to explain the mechanism. Here you may see a frustrated magnet as a class of quantum material, but would similar materials be helpful in climate tech? So let's see if we can fix the CCS industry with advanced quantum materials in 14 minutes. What's wrong with the CCS industry, you might ask? Well, carbon capture and storage, CCS and oil and gas operations are two sides of the same coin. In fact, 50% of human-induced seismicity is resulted from oil and gas operations. Here we can see how geological sequestration of carbon dioxide as part of carbon capture and storage CCS operations can induce seismicity. The carbon dioxide gas is liquefied under high pressures and then injected into geological formations. Oil and gas companies often do that as part of a process called enhanced oil recovery, OEOR. So they can extract more oil by injecting CO2. The induced seismicity threatens the integrity of the seal of the CO2, and the CO2 being less buoyant basically finds its way back up again in the air. So here, Oklahoma Carbon Hub is shown as an example. Although they are not located on active fault zones as we are here in California, they experience shakes resulted from these operations. Carbon dioxide pipelines do sometimes crack because of the high pressure of the gas inside, and that adds another layer of risk to such operations since the gas can be toxic in high concentrations. In fact, many residents in East Coast were admitted to hospitals because of such toxicities. So to summarize, CCS results in a small shake for us, but a large quake for the CO2 seal. On the West Coast where we are located, however, CCS is a relatively new phenomenon. A CCS project is being built in the Central Valley in California. This project was approved recently, but this location has a geological significance as well. Those familiar with California's seismic fault system know that we are living in the proximity of a giant fault called the San Andreas Fault. This fault is known to be responsible for great earthquakes in the history of this land. The probability distribution of such rare events show a frequency of approximately every 132 years, with the probability this decreasing over time, which many geophysical theories try to explain. Needless to say, CCS operations near this fault might have consequences. So let's discuss this even further. This is a creep rate plot which I created using satellite data. The San Andreas Fault, responsible for the 1906 San Francisco earthquake, extends south and runs beside the Salton Sea. Speaking of hydraulic pressure and policy errors, It's noteworthy that a failed irrigation project in 1905 related to Colorado River created the Salton Sea unintentionally in 1905. In other words, the Salton Sea was created as a result of a policy error. Unfortunately, a year after, in 1906, earthquake of San Francisco happened, which exhibited a magnitude of 7.9 with 3,000 plus casualties. The probability of large earthquakes have decreased since. Some theories suggest that the reason is that the Salton Sea is drying up and the weight of water pushing down on the fault is reduced. This is a very, very interesting system in California, so I decided to dive into it a bit more. These photos are taken a month ago, and here you can see the fault line as well as the San Andreas Fault Observatory at depth in Parkville, California. I used satellite data to get a sense of how creep rate at this fault varies with position. In fact, I realized that higher latitudes have higher uncertainty in creep rate, which itself maximizes around Parkville. This is the uncertainty distribution in creep rate, which by no means is Gaussian, given the heavy tails. As an experienced data analyst, you realize that, in fact, gamma fit would be a better choice, and that would produce 0.9 plus or minus 0.4 millimeter uncertainty as a representative value of this data set. In geophysics, fitting geophysical models to data is known as an inverse problem. Here, a well-known geophysical model was used, and using Markov chain Monte Carlo, MCMC simulation, I fit that to satellite data. In other words, from the D matrix here, I got the M matrix. So before showing you the results, let me talk about the method first. MCMC was pioneered by someone named Metropolis in Los Alamos National Lab back in the day when physicists were working on the Manhattan Project. Metropolis was invited to work on that project by Oppenheimer himself. This method today has numerous applications in many fields of science, including earth science. So here are the results. I chose to add two velocities together because just using one gave me a high RMSE, which is a root mean square error of 1.4 millimeter per year. And then remembering from the creep rate uncertainty distribution we saw earlier, 0.9 millimeter was expected. So also I asked a geologically knowledgeable friend here at IGPP who looked at their data set pertaining to the same fault, and they had 1 millimeter per year as uncertainty. So I also got two velocity values and got a lower RMSE, but just doing two faults model instead. And I can show you the results now here. You can see it fits really well. And the consequence was that I got two velocities this time. So one is 23 millimeter per year, and the other one is 14 millimeter per year with uncertainty of 1 millimeter per year. The fit is shown here. It looks really good. And the fault, the other velocity basically that I got is 14 millimeter per year. It corresponds in the literature to a fault called the San Jacinto fault, which is located east of LA in Riverside area. So that fault has a smaller creep rate, but is more active. Here is a summary of the values for the MCMC simulation I got. These are for velocities, X's are for relative location, and D is for depth. I even actually further improved the RMSE by applying a Kalman filter. Here's Kalman's algorithm, which is widely used in science and engineering when you are dealing with noise. Kalman received the National Medal of Science in 2009. So we discussed before that the noise distribution was non-Gaussian and there were some nonlinearities involved. So I chose an unscented Kalman filter instead, and I was able to reduce the model noise to 0.9 millimeter per year using this method, which now perfectly matches the expected uncertainty in the data. Using similar MCMC methods rooted in Bayesian statistics, one can come up with a quantified risk for CCS as well, predicting induced seismicity 4 hours before they happen. I have discussed these methods in my CSP report, but I checked my calendar and the year is 2025. I know the world is not perfect, but why not use quantum materials to seek better structural materials for climate tech? So here are my policy recommendations. I propose we engage the communities And that includes all people who live on the land and not just some stakeholders or interest groups. Combine experimental approaches with computational approaches. This could result in better reservoir engineering for CCS operations as well. But why not develop better materials for energy applications to reduce CO2 emissions and our China dependence at the same time? Unfortunately, some proposals to reduce CO2 are still heavily reliant on China, but we can do better. So let's follow the rabbit hole here. This is a recent article published on the US Department of Energy website. Researchers at Pacific Northwest National Lab created a new superalloy that swaps out cobalt for manganese. As you know, cobalt has many applications, especially in EV batteries and other advanced materials. This paper, which was referred to in the Department of Energy website as well as the Office of Nuclear Energy, has shown that cobalt can be substituted with manganese. And the good news is that manganese can be sourced from other countries, such as Australia. This in fact reduces our China dependence significantly. This work was published in an Elsevier Material Science journal. My own work in that field examines how properties of metals change with the temperature by relating their electronic behavior to their mechanical behavior. Well, when you touch something by hand, you are touching electrons, essentially. So mechanical properties are resulted from electronic properties. Doing so, I came up with a physics equation for the electron work functions. Since its publication, I have seen many interesting applications of this. Other physicists use my work to improve their physics experiments. This is an example of a PhD thesis in Germany which did so. By reducing error in their experiment, they were able to improve determination of the beta neutrino angular correlation coefficient in neutron decay. Such studies are very important in our quest to understand the universe. Looks like the industry is also catching up. Everybody knows that durable materials which can withstand high temperatures are crucial in fusion power reactors. Imagine how combining these equations with modern data analysis tools such as MCMC we discussed before can result in materials discovery. Some researchers in material science are already doing this. This, for example, is a GitHub repository developed by a friend of mine who is applying deep learning to materials with microscopy. Imagine how these can help better CCS reservoir engineering so that we don't have to engage in medieval decarbonization practices anymore. Thanks to these advanced quantum materials and the advancement in solid-state research, fusion microreactors capable of withstanding high plasma temperatures are also currently being built in this country. Microreactors are so small that you can probably just board them on a plane, So this ensures we focus on transition from oil and gas through development of advanced materials. The remaining challenges can also be addressed by better advancement in quantum materials in general. Well, like everything else, this research also needs continued support from the NSF and engagement with solid-state physicists like myself, without which we would lose our advantage in the competitive world of materials development. The funding in the year of 2024 for similar research is presented here. And then, as discussed before, advanced materials are already revolutionizing climate tech, and we should develop them even further. And thank you for your attention, and please stay in touch. I'd be happy to answer your questions. Go ahead.
So I was just wondering on this topic, what would be the biggest thing, like your biggest takeaway that you think was the most significant finding and something that you would like to see further expanded upon, going forward either by yourself or other researchers?
Well, I would say the most important finding is that electronic behavior of materials are related to their mechanical behavior. So we should investigate that research further, basically. And imagine what properties you can get. You can get exotic materials that you never had before, and that can change the climate tech industry as well. So you don't have to rely on fossil fuel anymore.
That was absolutely phenomenal. I was wondering, do you have any plans to further this research, like potentially with a PhD?
Sorry, what do you mean?
Like, do you have
developing? Oh yeah, this plan basically I have done some developments on this as well, and you can actually look on my research profile if you're interested. I have actually done more research on this, so if you're interested, you're more than welcome to look them up. Of course.
Thank you.
Thank you.